The mean annual cost of automobile insurance is $939 with a standard deviation of $245. What is the probability that a simple random sample of automobile insurance policies will have a sample mean within $25 of the population mean for each of the following sample sizes? First we'll do the sample size of 30, and then we'll do a sample size of 400. To be within $25 of $939, I'm talking about an interval between $914 and $964. And what I want to do is to find the probability that when I take a sample of size 30 and calculate the average on that sample, that average will fall somewhere in this interval from 914 to 964. Now, to calculate that, I need to find the probability of being in that interval, and we have a normal density function here because our sample is of size 30, and the central limit theorem says that we can approximate the sampling distribution with a normal distribution. And I'm going to use the normal probability density function in the same way that we did in chapter 6, the previous chapter. And what I'll need to do is to find the area under that density function above the interval, and that will be my probability. Now, to do that, the first thing I need to do is to calculate the z-score. Let's say for the 964. So I'm going to take that value and subtract the mean, 939, divided by the standard error. Now, the standard error is going to be the standard deviation and divided by the square root of the sample size. This is actually the standard deviation of the sampling distribution, and in my z-score formula, that's the value I'm going to need for my standard deviation. And when I calculate that, I get a 0.56. So my z-score for 964 will be a 0.56. And since I'm exactly the same distance on the other side of the 939, and the normal distribution is symmetric, I can go ahead and say that the z-score down with the 914 is a negative 0.56. Now, to calculate the probability that the sample average will be in that interval from 914 to 964, I need to find the area there under the density function above the interval, the area that I shaded. And I'm going to go to the table to do that, and I'm going to look up the 0.56 in the standard normal table, and looking that up and knowing that the table reads from the z-score to the left, the area to the left of the z-score, then I can see that this area, which I'm shading in blue, is given by the table as 0.7123. 0.7123. Now looking up a negative 0.56, the table is going to give me the area to the left of that, which I'm shading in green, and the table value is 0.2877. So, the probability that my X bar value is between 914 and 964 is equal to the probability, we'll change these to z-scores, that the z-value, the z-score, is between a negative 0.56 and 0.56, and that's equal to 0.7123 subtract 0.2877, which is 0.4246, or we can write that as a percent, 42.3%. Now, what have we calculated here? We've calculated a probability. The probability that if I would take a random sample of size 30 out of the population and calculate an average on that random sample, the probability that that average, that sample average, the X bar that I've calculated, the probability that that would be somewhere between $914 and $964 is 42.3%. There's a 42.3% probability that my sample average, taken from a sample of size 30, will fall somewhere within $25 of $939, or somewhere between $914 and $964. Another way I could look at that is that if I would take all of the random samples of size 30 that I could take and calculate the averages on each one of those samples, 42.3% of those X-bar averages would be within $25 of the $939. Now let's do the same thing, except we're going to change the sample size to 400. So my standard error is 245 divided by the square root of 400. And that number is going to be quite a bit smaller, $12.25. So the standard deviation of my sampling distribution is $12.25. Now we're still wanting to do this pretty much the same problem of finding the probability of being within $25 of the $939, which means we'll need to calculate the area under the density function above the interval. And the first thing we'll do is calculate the z-score of the 964. Pretty much the same thing we did with the last problem when the sample size was 30, except for the standard deviation is now $12.25, the standard deviation of the sampling distribution. And this then calculates to a z-value of 2.04. And by symmetry, we have 2.04 z-score for the 964 and a negative 2.04 z-score for the 914. So these are the values that I will need to look up in the table as before, and to calculate my shaded area there, which is the probability of being in the interval from 914 to 964. So let's look up 2.04 in the normal table. And if I do that, it's going to give me the area here that I'm shading in blue all the way from that z-score to the left end. And the table value for that area or that probability is 0.9793. And then looking up a negative 2.04, which I'm going to shade here in green, is 0.0207 probability. Now again, I want the area over my interval that I shaded in black. So to get that, I'm going to take the 0.9793 and subtract the 0.0207. So the probability in this part with a sample size of 400, the probability that my sample averages that are calculated from those much larger samples will fall somewhere between $914 and $964, or within $25 of the $939, is the probability that the z-value will fall between a negative 2.04 and 2.04 will be 0.9793 subtract 0.0207, which is 0.9586, or 95.9%. So what we've done in this problem is to look at a sampling distribution. A sampling distribution is a distribution of sample averages taken from samples of a certain size. In the first part, we looked at samples of size 30. And the sampling distribution then is the collection of all the sample averages that you would get from taking samples of size 30. The central limit theorem says that if the sample size is 30 or greater, then you can approximate the distribution of all the sample averages by a normal distribution. So we did, and we used the probability density function, the same one that we used earlier in the last chapter, to model that and to calculate our probabilities. The last part of this problem is we developed another sampling distribution of sample averages, but this time the sample averages were taken from much larger samples, samples of size 400. Again, the central limit theorem guarantees that that sampling distribution is normal, and we use the normal probability density function, the way we did in the last chapter again, to go ahead and calculate the probabilities. In using a larger sample, the standard deviation, or the variation of the sample averages, is reduced. And we can see that by using our standard error formula, that it goes from 44.7 down to 12.25. A larger sample will have a tendency to produce sample averages that are better estimates of the overall population average and would tend to overall be closer to that value. We can see that in our probabilities that we calculated. For samples of size 30, 42.3% of those sample averages would be within $25. But for samples of size 400, the sample averages that are calculated from them, 95.9% of them would be within $25. This is a common sense issue. The larger the sample, the better the average from that sample is going to estimate the population average. The tendency is that those sample averages would be closer to the real value than sample averages taken from samples of size 30. So our probability goes up when we increase the sample size.